Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to our inaugural webinar for the calendar year 2020. And we're very pleased to have today a great presentation on pipeline leak detection, overcoming difficulties in validation and verification. And as our presenter, we're very privileged to have Dr. Chris Minto, who is engineering director with Opta Sense and is responsible for engineering, product development, and research across the group. He's been part of Opta Sense since 2008 and has been involved with a number of their product delivery. Most importantly for us at FOSA, he was our first chairman of our technology committee and really set for his tenure a really high bar, and also in terms of the quality of the work that he did, but also did a great job of integrating representatives of our various member companies. So we are very appreciative to Chris for all that he did and really providing thought leadership in this space. So we are certainly looking forward, Chris, to your presentation here today.
Well, thank you, Mark, for those very kind words indeed. Good morning and good afternoon, everybody. As Mark says, I'm Chris Minto with Opta Sense. We're a fiber optic based system, and we do an awful lot of pipeline leak detection. Focus of my talk today is looking at how we validate leak detection technologies, comparing external systems where the fiber optic is outside the pipe to how this is more commonly done with the more run-of-the-mill, everyday computational pipeline monitoring techniques, which are internal techniques. They measure parameters inside the pipeline. I'll start with just saying a few words about Opta Sense. We'll go on to look at how leak detection is affected from fiber optics. I'm not going to spend much time on that because it has been covered elsewhere beforehand. But we'll look at the validation and verification options, and we'll present some of the exciting ways in which we've been approaching that over the last 12 months or so. So first, just a couple of words about Opta Sense. We're a large fiber optic sensing company. That's our core, that's our focus. But we are very vertically integrated, from the narrowband solid state lasers that are the heart of fiber optic sensing systems. We produce them out of our Santa Clara factory in California. We develop and manufacture a range of acoustic sensors, interrogation devices. We develop our own scalable architecture for spanning some very large distances. Our largest projects around 1,800 kilometers long. We take a systems approach design. We don't just stop with the sensor. We go down into the cable itself, and we do a lot of development on very specific cable and fiber optic methodologies to try and get more out of the sensor than the interrogator can do on the end. And then finally, we have quite a lot of resources dedicated to signal analysis, signal processing, seismic analysis, etc. So we cover the full range. We're wholly owned by the Kinetic Group, who are a global multinational, split pretty much 50-50 between the US and the UK. Within Opta Sense, we have sites in the UK and the US and the Middle East and Canada. Okay, so this is the range of areas that Opta Sense concentrates on. We're a platform technology. So today the focus is pipeline monitoring, but we get involved in a range of other disciplines as well. And this brings benefit, as we can see problems in one sphere may be able to be tackled by solutions in another sphere. So a quick word about conventional approaches. So the conventional, or as it's generally termed, internal approach to leak detection involves taking sensors that are either strapped to the pipeline or more commonly have access to measurements of the pressure or the flow within the pipeline, and essentially looking at how these change along the pipeline. And so if you've got condition 1 over on the left-hand side, a high pressure or a known flow rate, but over on the right-hand side, which may be tens of miles away, those conditions have changed, we can do statistical analysis on the results of many parameters or many point sensors and try and predict whether a change has happened and where it may have occurred. Such systems are generally characterized by a small number of sparsely distributed sensors, each requiring power and communications and a statistical modeling tool that sits on the back of it. So in general, they're very well adopted, very well accepted as providing a good approach to leak detection on pipelines. But they can be quite slow when working at their highest precision, looking for the very smallest leaks that require time to statistically average out the evidence, and their positional resolution will not be very good because, of course, they can't be everywhere. And this is one of the key advantages of a fiber optic. So borrowing a couple of slides from FOSA, from some of our general sensing presentations, what is distributed fiber optic sensing? I think a lot of our audience will now know this. This is using a fiber optic cable that will be positioned along the asset, taking a spare single core of glass fiber within the cable and sensing on it from one end. In our case, we're using the Rayleigh backscatter, or distributed acoustic sensing as it is commonly known. And what this enables us to do is, from a single location, look both upstream and downstream down the pipeline and turn that piece of glass into a very precise sensor of the acoustic field. And this gives us thousands of sensing points. It's truly a distributed technology. So typically over 25 kilometers, or sorry, 25 miles or 40 kilometers, we can deliver thousands of sensing points, each being multiple feet or small numbers of meters long. And each of them, we can gather information as to what is happening outside the pipeline and look for the presence of a leak. And I'll explain how we do that. This sort of illustrates the typical methodology. We fire a short pulse of light from a coherent laser down that single core that we may be adopting. We may have borrowed it from a cable that is there for communication purposes. And we look at the backscatter signal that is the echo from the glass itself. We can pick up the acoustic field from very low DC frequencies up to kilohertz frequencies, and we can process that to look for the sounds of, or the feel of, different behavior that is taking place. At the low frequencies, we can pick up strain and temperature information. At the higher frequencies, it's vibrations and acoustics. And with an engine that looks at the evidence of each of these measurands in each sampling point along the fiber, many thousands of them all at the same time in real time, we can look for the evidence of a leak. Where is the fiber? So as I mentioned, it might be a third-party cable that is there for other purposes. Where you would put it depends on the type of leak detection you're doing. If you're working on an above-ground pipeline, the best place is taped to the side of the pipeline and perhaps strapped as well. Place it on the opposite side of the pipe from the prevailing wind direction. For a buried pipeline, the orientation is not so important. It tends to be governed more by what is easy to access. What affects the performance most is how far away from the pipeline it is. Closer to the pipeline means being able to sense smaller leaks. With an architecture based on repeated instances of interrogation devices, which each of them will maybe cover up to 50 miles, looking upstream and downstream. Repeat that at instances along the pipeline, and then you will have your whole pipeline covered with sensors every 10 meters. They can be pulled together on a networked backbone and the data accessed anywhere with lots of interfaces, as is commonly used in the industry. So our approach to leak detection takes in 4 different measurands. The first is when a hole is created on a pipeline and the fluid, either liquid or gas, that is constrained is able to escape. A negative pressure pulse and under pressure shrinkage of the diameter of the pipeline travels in both directions, up and down the pipe, and we can visualize that. We can feel it from outside the pipeline as a vibration. The noise of the product escaping from the pipeline is very characteristic, creates a broadband noise that we can pick up. We can pick up the temperature changes caused by either a heated product encountering the cable itself, or potentially from a gas product leaking and causing Joule-Thomson expansion and local cooling of the ground, and again in the vicinity of the fiber. And then finally, particularly important for a gas pipeline, you may get some lift or ground heave as the gas escapes into the porous soil, or indeed in a liquid pipeline where the fluid is pushing on the cable itself. And all of these can be accessed. Some of them, as you'll see through the presentation, operate quicker than others. Comparing to the industry standard nomenclature called up in the API recommended procedure, sensitivity, reliability, accuracy, and robustness. The fiber optic, the attraction of the fiber optic sensors is that their sensing floor is adaptable to very, very small leaks in small numbers of liters per minute, and being able to deliver an answer in seconds, compared with a computational technique really limiting at around 1% of flow, but taking tens of minutes to deliver an answer. The fiber optic potentially could be 2 orders of magnitude more effective in terms of overall detected spilled volume. Reliability, that's the focus of quite a lot of the talk that I'm going to go through, the probability of detections and false alarm rates. The focus of this talk is validation, so we're going to focus on that. Accuracy, because we've got sensors everywhere, the positional accuracy is very, very strong indeed. Robustness, they're able to withstand dynamic changes in the pipeline. That's perhaps a little bit unproven at the moment because the adoption is still in fairly early stages. We know that they are quite adaptable to a range of conditions because they're not directly experiencing the conditions in the pipeline, but we also know that some effects from the pipeline, such as startup and shutdown, may create signals that need dealt with. So our key points. The leak rates that we're going to talk about will be measured in liters per minute, not percentage of flow. And that's because rather than looking for a change in flow conditions, we're actually looking for a product that's escaping from the pipeline. The bigger the escaping amount of product, the easier it is to detect, naturally. We operate 2 different modes. Out of the 4 that I've shown you, the fastest and the most sensitive is the negative pressure pulse. It's a very unique indicator of a leak. We can deliver a result in tens of seconds, and it's very evident even for the very smallest of leaks. We then back that up with a fusion of all of the other mode options, or the pairing of modes, either with or without NPP being included, to provide a little bit more confidence, but that tends to operate at a slightly higher level of leak detection, around 150 liters per minute. Still, we're talking here order of magnitude quicker than conventional approaches. Okay, so that's the background on leak detection, how we got to where we are. Let's focus now on the approaches to test that are available. So for an internal system, there are essentially 3 approaches. Doing a full fluid withdrawal test. Those are expensive. You don't do them in many places, so they're not done often. The second 2 approaches are both elements of modeling, either a full leak simulation model where you can propagate statistics through a virtual pipeline. Again, they can be quite costly to set up, but they are very precise. And then at the very low end is functional parameter testing. Switch off the result from one of your sensors and follow the flow of alarms that propagates through the system. That can be done quite quickly. So how can we compare to that with our approach? So The external systems are very different from the internal systems. We're not measuring flow parameters point to point. We're measuring the acoustic field and interpreting those results. But we still need to be able to demonstrate that our systems have a reliable probability of detection under different conditions. We have to demonstrate the alarm rate, and we have to confirm the reliability. That's a whole validation piece. Do the systems that we offer meet the specs that we say they will provide to you in real life? I'm going to focus on validation first, and then we have a section on verification, looking at when we've installed it with a client, is it operating as intended? How can a client know that their system based on a fiber optic cable is delivering the results day to day, month to month? One of the constraints that we've got on validation is if we're using this negative pressure pulse mode, we really need to see that pulse develop and move out along the pipeline over a reasonable length, typically about a third of a mile, 500 meters or so. We also want to, if we're going to create leaks on a pipeline, which as you'll see is part of our validation approach, we want to be using burst discs rather than valves, as valves take too long to open and the effects are diminished quite considerably. We're going to operate a leak. We have to maintain it for long enough for the system to be able to see it and respond within its sort of defined parameter space in terms of response time. We also have to think about ground settling and relaxation. If we're spilling fluid into the ground, how does that affect the next test afterwards? So let's have a look at how some of that has been done to date. So over the past 5 years, there's been a lot of really good approaches to leak detection. There's been a number of industry consortia tests that have been run, and a lot of operators and a lot of vendors have participated really well in this, and it's helped grow the knowledge of how these systems respond. And they have a lot of benefits. These have generally been lab-based tests. There's not been an awful lot of in-field tests because nobody wants to take a pipeline and make a hole in it, which is fundamentally what you need to do if you wish to exercise it completely. But these tests have been really good at looking at sensitivity, the ability to detect at range, the time to detect under fairly controlled conditions. But they've generally been limited to lab-based tests. They've been short distance. They've not necessarily been able to look at flow conditions in the pipeline. And similarly with on-site simulations, those have had some limitations in terms of, again, by injecting fluid into the ground, you're not truly representing what goes on in the pipeline itself. And the conclusion from all of these is systems can be set up to detect the tests, but the tests are generally not an accurate proxy to day-to-day operations. We rank each of these validation solutions that we've participated in, and we looked at high pressure lines mounted inside shells, full bore tests, pipeline extraction tests, etc., etc. And we came to the conclusion a couple of years ago that really if we want to validate our systems that were out being deployed with clients, we needed to go and take a pipeline and make some holes in it. We felt that is the only way to truly validate the system performance. And that's the focus of what we're going to look at next. Full-scale leak detection in a pipeline, in a buried pipeline, doesn't come easily. There's not many places in the world you can go to go and carry out this sort of work. You want somewhere that has got a full bore pipeline, or at least a representative bore size. You want to be able to change pressures, you want to be able to change flow rates, and ideally change the product from a liquid to a gas. We think these elements are all required for true validation. We started with doing some work on above ground pipelines because our system will support both. In 2017, we went to the Sintef facility in Norway, the large scale flow loop, which you can see here in the bottom right. It's a long 2.5 kilometer flow loop. We created a spool piece that we cut into the main flow loop that allowed us to create with actuated valves, control jets, and make leaks to our wind. I'm not going to talk too much about the above ground. The focus on today is really going to be the below ground and the work we carried out through 2019. Talked about the 2017 work earlier, and we do have a white paper on it for anyone who's interested. So to carry out the below ground work, we looked for a useful validation facility, and the most appropriate one we could find was the CTDUT pipeline test facility situated outside Rio de Janeiro. And this is, again, it has all the requirements that we've noted as being important. This 2.5 kilometer or so length of the flow loop. It's an out and back arrangement, as we can see from some of these diagrams. And we've conducted, during 2019, 2 sets of full-scale leak tests. So here's the facility here, an aerial view from Google. There's a pumping facility down on the southern side of the diagram, and then the flow goes up a hill, down into a saddle point, up another hill, returns down the second arm, and returns back, and so on, round and round in a flow loop. Large scale flow loop indeed. And we carried out our testing here, just below the peak of the first hill before the saddle point. That isn't necessarily specific. It was more about finding good ground that we could be able to work on. Some of the ground was a little marshy. Being able to find a representative soil location that was easily accessible, and we had a service road to allow us to get there. The subsurface orientation of the tests, I mentioned we had the upwards flow on one side, 12-inch diameter pipeline, downwards flow on the other side, separated out by around 1 meter to 1.5 meters. The flow loop is buried about 1.2 to 1.5 meters down, and the fiber optic cable is an unarmored, pretty standard telecoms cable in a duct that is oriented around about 0.5 meter to a little bit more. For most of the travel around the loop, it's around 700 to 900. In the flow section, as we excavated it, we pulled it in a little bit to around about 0.5 meter, which is where we specify our performance. There are variations as you move it out and back. So what we did for the tests is created a 10-meter spool piece with different leak ports in it. We wanted to look under this range of conditions. We looked at a range of hole sizes, 1, 3, and 10 millimeter, and a range of orientations. So we cycled those around so that at each point, each test location out of the 7 available, we had a range of parameters that we could explore, which then lent itself to a range of tests. We did some work on the pit to help it drain as well. So we weren't going to be working in stagnating water, allowing us to increase the rate at which we carried out tests. But essentially, you do have to guard against washout, etc. So we wanted to make sure we could progress at all these different orientations and different locations down the flow loop. And you can see here the construction taking place. The leak valve arrangements are important. We did mention that, so we needed some lockout and control valves. We needed to have a bit of double protection on there, so if anything went wrong, we were able to lock it off and the whole flow loop wouldn't drain out. I mentioned the importance of a burst disc, and the arrangement at the end was to use a burst disc together with an orifice plate. So the orifice plate was creating the governing of the size of the leak, and the burst disc would allow the leak to only occur instantaneously as it would as a failure in a pipeline at the governed pressure. And typically we're working about 8 bar. And so that gave us 2 options. We could either open the valve and expose the high pressure fluid to the burst disc and have an immediate failure, or we could reduce the pressure in the flow loop and then slowly ramp it up until we reached the failure point. And the discs were really very effective. They failed bang on the pressure, so we were really very pleased with their performance. We did a range of tests, as you can see here, 1, 3, and 10 millimeter, and this is over the 2 visits that we paid to the site to carry out these sets of tests. A range of pressures from 5 up to 18 bar, which in turn provided a range of flow rates reported here in liters per minute or gallons per minute. The site itself fully instrumented, and so we were able to get all the parameters, of course, of the flow conditions as they were occurring. And we were even able to do some mixed phase work, which is not really the subject of today. I mentioned some of our parameters, so we quote the performance of our leak detection for the negative pressure pulse down to around 15 liters per minute, which you see here, one of the higher cases for the 3 millimeter diameter, and the main integrated case at 150 liters per minute. You'll actually see from the results that we did rather better than we specify, but we always like to err on the side of trust and caution. So let's explain a little bit about the geometry then. So this is the same aerial view of the site, and I've numbered a few different points. We're going to look at the results from the negative pressure pulse. So can we detect an instantly failing burst disk from the negative pressure pulse that it creates? It's a slightly complex environment because the negative pressure pulses can travel many kilometers in a pipeline, and this one was, whilst suitable size for our needs, it's still only 2.5 kilometers long. So this is the live waterfall trace from one of our negative pressure pulse burst events. We're looking on the x-axis is distance away from our operating base, and the fiber goes up to the end, and then it loops and comes back inside the same cable, just using a different core. And then this is time, and then we have intensity just color coded. So we can see where the failure happens. Well, it happens twice, which is confusing. And that's because at point 2, that's the top of the hill where the flow loop turns back round and the fiber turns back into the same cable. So essentially we have 2 passes. So we see this V shape, the negative pressure pulse, extending out on the first pass of the fiber and then on the second pass of the fiber. Now I could have just shown you the 1/2 and it might have made it a little bit simpler. The interesting part as well that we should note is if we look at the second observation for it here, we see that the pulse goes back to the bottom, point 3, which is at either end, and then comes around the flow loop and starts traveling back up the other pipe. And similarly, from the top, it also goes up to the bend and goes round the other side as well. So on these 2 sections, we're actually viewing the leak in the second part of the pipe, the downwards pipe, which is about 1.5 meters away. So it's not just a short range technique. We see it closest here where the fiber is about 0.5 meter away, but we're also seeing the effects of it in a neighboring pipe where it's already traveled about 1 kilometer and the fiber is about 1 meter away. So it's a very effective technique indeed. So here's an illustration of the importance of the burst disk. The top image, which is the one we saw earlier, is from a 3 millimeter leak at 10 bar, pointing downwards away from the fiber. That's operating with the burst disk. Then the same port, the same 3 millimeter port at 10 bar, operated after, so that we closed the valve and just opened the actuated valve, hydraulic valves, not manual operated, but we can see that even with a hydraulic valve, the negative pressure pulse is much, much smaller than the instantaneous failure. And this is because the rate at which the release happens. With a burst disk, like the wall of a pipe, the failure is immediate. With a valve, they have an actuation time to rotate. And that slowing down of the orifice developing leads to a much weaker effect. And so it's not really practical to carry out these tests with an actuating valve. You really need the burst disc if you want to replicate the true failure of a pipe. Otherwise, you make the job that much harder, or it makes it appear that you can only detect a much smaller event. It's also considerably more variable. This is how the orifice noise looks. So the negative pressure pulse was the first mode, the orifice noise was the second mode. So here we're looking at one location. In the previous graph, we were looking at all of the locations and just looking at the signal intensity over time. We've now chosen the leak location, and we're just looking at the frequency content at that location and how it develops over time. This allows us to really easily see the start and the end of the leak and how it changes. It's not constant over time. We can see that as a cavity essentially around the leak port is developing, the signal builds and builds and builds. And then finally we shut it down. This was with, again, a fairly large 10 millimeter at 10 bar. But even with a 1 millimeter orifice at 12 bar using compressed air in the flow loop, the same signal structure is very visible. And so it shows how you can apply these either to gases or liquids. With the other two techniques that I mentioned, the strain behavior and the temperature change, those are most easily visualized by looking not at the dynamic behavior, the acoustic information, but by looking at the DC, the raw output level, the strain information. So you can consider the acoustic information to be vibrations on the DC level, essentially. And if we look at that, we can see that after a leak occurs, we first start to see this signal developing as strain appears on the fiber itself, from the cavity, from the pressure of the fluid escaping. And then over slower time, as the temperature of the fluid starts to change the temperature of the surroundings and the temperature of the cable itself, we then start to see this sort of downturn. And so by applying different frequency filters to look for these two types of content, it gives us a little bit further power and a little bit more confidence that what we're seeing is a leak. All of these we can display graphically. The negative pressure pulse I've not shown because that's just an instantaneous, is it there or is it not? But it's indicated by this red line where the leak was initially recognized by the negative pressure pulse. With each of the three things, we see first the orifice noise, we see a low level, and then suddenly, as soon as the leak starts, it starts building and rising, and then we reach the end. And there, the green cross illustrates the alarm from the orifice noise appearing later than the alarm from the negative pressure pulse. And then similarly with the strain, fairly short duration strain effect, but the temperature change, it takes a lot longer to build and then a lot longer to die down, illustrating the sort of soil saturation type conditions. But all of those have got their alarms, can be made to trigger and help the operator have some confidence by having trending information that they can look at. It's not just an alarm on a screen saying leak. There's further levels of information available. So looking at the performance results that we achieved from the full-scale tests, for the negative pressure pulse, as I mentioned, we specified down to 15 liters per minute. These are all of the tests that we carried out a burst disc negative pressure pulse test with. Out of all of them, the first ones here we missed on each pass of the fiber. So looking up the flow loop, down the flow loop, going through a coil, a delay coil, and then passing up the flow loop again. This first test didn't develop an NPP at all, and we think that was actually a failed disc that had failed during the deployment or through a manufacturing issue. We're not quite sure, but it didn't really develop a signal at all. So there wasn't a signal that was present for us to miss. In all of the other ones, apart from one on the longest pass, we achieved an immediate detection. And so you can see from some of the numbers here, these are about an order of magnitude lower than that which we specify. So we were very pleased with that. And that gave a very high probability of detection, 38 out of the 39 if you accept that we ignore the first 3. So again, very pleased with the performance of the negative pressure pulse detector. We carried out the performance evaluation on the fuse performance as well, the 150 liters per minute, and looked at the number of leaks, genuine leaks that were recognized, and the number of nuisance alarms there. We didn't carry out many that were over the 150 liters per minute, but we did detect all of them. So again, we were happy that this validated the initial performance basis of the operating conditions, doing that on a truly representative pipeline. So where does this place our fiber optic system in terms of performance? How can we compare that to a conventional computational system? I've tried to represent that here. It's quite difficult because systems will operate in different ways in different regimes. So I've mentioned earlier, we focus on liters per minute, the leak rate itself. In traditional internal technologies, they tend to refer it as a percentage of flow rate. And this is because it's a statistical mechanism. You can take longer to average at the lower percentages, whereas if you're looking for a large leak, you'll operate on very short window sizes. Smaller leaks, much larger ones, but the technique limits are around 1% or so. And this is where we've tried to show here how the computational CPM approach works. Different gatings for different window sizes. So for ruptures, it'll trigger in tens of seconds or minutes, but for the smaller leaks, the 1% or so, it's tens of minutes. And so I've overlaid on here where our 4 modes have their applicability. For the negative pressure pulse, we've shown how that has, well, we specify down to the sort of 15 liters per minute. That's about 0.1% in a typical transmission pipeline. The results we've showed even push that further down off the graph, but we try and be cautious here. The orifice noise, we've shown that requires, well, these other modes require around about 150 liters per minute. So that's operating again similarly around the sort of 1% level on a transmission pipeline. But these will deliver their answers in seconds again or minutes. We really stop our operations after around about sort of 5 to 10 minutes of windowing, and so we don't really go into the longer durations. And so what this gives you is both the ability to sense much smaller leaks than are conventionally available, and at the same time deliver the results from all of the approaches much faster than is conventionally available. And then this lends itself to a reduction in overall leak size. And that's what we present and then specify as our typical sensitivities and response times. So that was validation, and we publish a white paper on the subject. We'd be happy to share if people want to get more detail and get in contact. I also want to talk about verification. So we think validation, the only way to show that an external system will meet its spec is to go and take a pipeline and make holes in it for real and see if you can detect them. That's not possible on a client site, and so we've also spent a lot of time over the last couple of years working on our approach to verification. We have a range of different approaches, much like the CPM approach that I talked about at the beginning with the modeling and the withdrawal tests. We have different approaches from alarm injection, which is just simple GUI-based filtering, through to end of fiber stimulation, ground probe injection, and valve burst disc testing. I'm going to look at some of these in a little bit more detail, but basically the more complex, the more you can achieve. And tends to follow then that the cost would also increase. And so the recommendation is that a mixed approach is needed, of a mixed regime of testing to cover the different aspects. So the first approach I'll mention, I'm going to gloss over the alarm injection. It's good for verifying linkages to other third-party systems, but we won't dwell on it. The first approach is end-of-fiber signals simulation or stimulation. Basically, we attach a box to the end of the client's fiber, which has in it some further fiber that we can then subject to. We can create realistic signals on the fiber itself using a stretcher, a fiber stretcher. We can input an orifice noise signal to the fiber, a signal that we've recovered from validation. Similarly, a temperature change and a strain signal directly onto the fiber, which is then connected to the client's fiber, which ultimately is connected to our interrogator. So it's a single unit, it's a single location. It's you could splice it in at a block valve location, you could put it to different places, but it's a fake leak you're creating. But nonetheless, it's easy to achieve, it's quite low cost, and that allows you to validate any of your units. You may have more than one on a system, to verify that it is working as intended. Connect the system up, run the test, demonstrate that the leaks appear as you would intend on the GUI. We talked a lot about the negative pressure pulse. That is very, very hard to create in the pipeline unless you actually remove some. Now, we don't want to make holes in pipelines. Of course, that's a terrible idea, but it is possible to create a fluid withdrawal through a burst disc. So at a valve site where we have access to the pipeline with control valves, with the burst discs, which are very simple affairs, run them through an orifice in the same way, extract the fluid and run it into a storage tank. This is quite possible to do, and we've done this with clients. It requires a little bit more planning, a little bit more thought. There's a little bit more client cost, and you can only do it where you have access to the pipeline at valve locations. So it has a limitation, but it does allow you to verify that as soon as you run your burst, you are detecting a negative pressure pulse. And it is verifying other locations because you are detecting that negative pressure pulse up and down the pipeline. It's not being detected fundamentally at the location you created. The fluid injection into ground, that's the last topic that I'm going to cover today. We've been developing a specific system to allow us to create the appearance of a leak next to the fiber on the other side from the pipe in the ground in a controlled manner, in a safe manner, that allows us to replicate the same validated signals that we've gathered from real life activities. And so we've worked with reputable industry partners to create this. In its first phase, we're doing gas injection via probe into the soil. With very simple, where the client will produce the compressed nitrogen, which can come in a palleted bottle rack. We connect that up to our gas regulation system. It'll work up to 100 bar, delivering up to 12,000 standard liters per minute. So we're able to cope with some very big flow rates. With an offset of safe tubing, we then, through some controlled process, it has to be followed fairly accurately, put the probe that we mandate the description of the probe into the ground at the offset from the fiber, and then with a safe system at work at play, we can happily create injected leaks to the client's specification. And if we're matching our minimum specification and we're able to detect the modes that are resulted, so the ground heave and the orifice noise, possibly some of the temperature change work, we've got a mechanism to verify the other three modes. So if we were to do the negative pressure pulse via a burst disc, we can do the other three modes via the fluid injection, gas at the moment, but we hope to follow with liquid quite soon. We then have now got a mobile field mechanism for verifying leaks. And here's some results from that. As you can see, there's the initiation of a leak on the waterfall. There's the spectrogram from the leak location. And as you can see, it behaves in a similar manner to the validated leaks that we covered earlier from the CTDUT test facility. So to conclude, we have a large number of our systems that are out there in the world, and until we had carried out this work, we always had at the back of our minds, how do we really validate this to make sure that we're selling systems that customers can rely on and believe, and that we can as well. We've obviously participated in a lot of tests up until then, and we had the confidence to sell our systems, but we wanted to make sure that there was a proper validated set of test results. And this isn't easy to do. It's one of the things that FOSA has been looking at over the last couple of years through the technical committee, looking at the needs of pipeline leak detection validation for fiber optic systems, and calling for the creation of a similar test facility in the USA. And that's getting some traction now, and we'd be strong supporters of that at Opta Sense. But we're out there at the moment doing leak detection around the world, and we needed to take action to show to industry, to our industry partners and our clients, that our systems can be validated. So we followed the steps here that were presented today, and this will be up on YouTube. You'll be able to look at this yourself in a little bit more detail, that we think is the minimum that is needed to show that your system can work. It's a major commitment in time and capital. It's not easily done. We've had a lot of sleepless nights, but we're really tremendously pleased with the results that have been shown. So we believe we've validated our leak detection system, and we're happy to share these results with the world. On the back of that, we've also produced 3 verification techniques to try and help clients. Once they've got the systems in service, how are they then going to continue to demonstrate to themselves that the systems work? And that can be achieved through either a range of client support activities, or we can also pass those abilities on to the client themselves. The benefits of leak detection are clear. We hopefully, as an aside from this work, have shown the improvements in sensitivity that can be gained from a fiber optic based leak detection. The positional accuracy that can be achieved is one very key measure, and we think that this sets a great direction forward, not just for us, but for industry to follow, in terms of stepping up a level so that we're at the same and similar level of validation as CPM systems. We have some resources available on YouTube. We've covered some of the work that we've been doing at the CTDUT facility on a couple of videos up there on our Opta Sense YouTube channel. I'd encourage you to look at that, and my contact details are there. So I will thank you at this point and hand back to Mark.
Thank you very much, Chris, and thank you for a very informative presentation. To ask a question, I see we already have a number, but just simply text that in, and on the box on the right, and I will be able to forward that. We had some interest on the negative pressure pulse issues that you discussed, and one of the follow-up questions was getting a handle on what the time scale is. What is the time delta between the detection of the negative pressure pulse and the detection of the orifice leak event?
That's a very, very good point. So the two will start to occur at exactly the same time. So as soon as the leak occurs, the negative pressure pulse kicks off, and it travels up the pipeline at the speed of sound in the pipeline. So in a liquid, it's about 1,400 meters per second in oil, and in gas, somewhere between 400 and 600, depending on the nature. And so it takes a very modest amount of time for that signal to pass along the pipeline. We're looking at it over a few hundred meters. And so it's initially pulled up into the system in seconds, We quote a sort of a 10-second delay on the detection of the negative pressure pulse, the original mode 1. With regard to, but typically it happens a lot faster. You're either going to see it very quickly or not at all. With regard to the orifice noise, I showed you that ostensibly starts from the onset of the leak, but it does require a little bit of time to build up to full intensity. And so for our fused mode, we quote up to 5 minutes as the maximum that we would pick up the fused detection from the various modes. And again, hopefully I've given the impression that we like to sort of overperform on what we quote. Typically, we've saw that at CTDUT within 1 to 2 minutes of the leak occurring.
We've actually got a couple of questions sort of on a similar point, but what fluids did you use for your leak tests, and really how do those fluids, I mean, you mentioned water, were there other fluids, and how do those differ from real life?
Yeah, so again, very good point that I should have covered. So the fluids we used were water as a proxy, well, either for water, because we do leak detection in water pipes, or as a benign proxy for hydrocarbons, and compressed air for the gas. The main difference for us on a technical basis is the speed of sound in the fluid itself. So we're now at 1500 meters per second for the water. For the actual sort of spillage activities, they really are, a modest function of viscosity. So we think the deltas from water to oil on the orifice noise, for example, are very small indeed. And we participated, as I noted earlier, in a lot of the other research-oriented laboratory tests to have the evidence that we're happy that true hydrocarbons are still detectable with the techniques. What we're unable to do is pull all of a true hydrocarbon leak together into the field for obvious reasons.
Thanks, Chris. Now I'm trying to, there's actually a question about test range. And I thought I heard you talk about 40 kilometers. What was the length of distance that you had? This question is, did OptaSense run tests at range beyond 20 kilometers?
So that's a good question. No, so we were slightly constrained by the number of available cores, essentially. So we did our first pass, would have been around about a kilometer, and then you saw the second pass at about 1.5 kilometers. We ran it then through a 20-kilometer spool back up. So we were about 21 kilometers all in all. It would be good to go back and test at longer distances, but that gave us enough at least of a trend.
So that was really the distinction, is the test was limited at 21, although the potential is for going longer.
Yes.
The presentation concentrates on below ground, but mentions above ground. What are the key differences in the sort of between those kinds of environments?
Yeah, that's another good question. So in the above ground leak, you don't have all of the same range of signals accessible to you. And you may have to concentrate on maybe just even 2 of them. So the negative pressure pulse will still be present. However, depending on the construction of the pipeline, you may have a large insulating layer, for example, so it may be diminished somewhat. And so that will affect the size of the leak that you're able to detect. Because the environmental strain and the temperature delta effects are really dependent on the fluid interacting with the fiber, unless you happen to have that taking place, and you probably won't, those modes really don't serve a useful purpose. The other one, though, is the orifice noise, and the leak from the pipe, either directly from the pipe or through the cladding, through the exterior shell, is still going to create an abnormal noise. There is some obvious dependency on wind conditions, which is why the negative pressure pulse mode, again, is really a very good mode to use. But in our published work on above ground pipelines, we tend to advocate NPP coupled with OFN, unless there are some specific conditions that would suggest otherwise.
Chris, there have been some injection tests in the past that have been criticized as unrealistic. Why is the injection tester that you devised better? So what's the nature of the improvement?
So it's I wouldn't necessarily say it's an improvement. It's about orientation of the parameters to suit what it is you're trying to do. So you have to be aware of the range of signals that you're injecting into the ground for a start. You're not going to see a negative pressure pulse, and so this is why, as the overall verification methodology we're recommending, it is essentially as a multiple pass. Use the fluid withdrawal from a valve assembly to verify that your NPP is occurring, and then use a fluid injection to give you some mobile mechanism to be able to exercise some of the remaining modes. And it definitely isn't perfect. And so, for example, you're going to be so limited in terms of the volume of gas or liquid that you have available to inject into the ground. You may not be able to see the temperature effects because they may not percolate through to the fiber. They're quite a short range effect. And the strain and the orifice noise, they tend to be a little bit more reliable. So it's definitely not perfect, but I think as part of a holistic program of test, it's really the only way to be able to reliably produce the same effects. And what we have done, perhaps the key difference we've made, is to aim for the sort of flow conditions that are parallel to the specifications that we offer.
So we're coming up towards the hour, so I'll give you one last question, and maybe it's less about the test, but more about adoption. What do you see as being the significant factors preventing widespread adoption of fiber leak detection in North America? And I guess North America really is the focus of that question.
Yeah, so in North America, the biggest issue so far for retrofitting for brownfield sites has been the lack of fiber. And I know there is a lot of good work going on looking at techniques on how to retrofit. This work might offer some assistance into that by looking at the negative pressure pulse mode again and how that may be able to be used at a slightly greater offset than typically we would recommend for all of our modes. That may have something to offer there, but getting the fiber close to the pipeline to be able to carry out the task that we've described here is obviously much easier in a new build. So there's definitely some great work going on in the USA at the moment. There's an eagerness with the operators to adopt this technology. We're seeing a lot of great projects coming through our doors and through our sister companies in FOSA. There's an awful lot of great work happening right now, but the lack of fiber to operate on has certainly been a bit of a hindrance.
Thank you. We do have some more questions, but we're coming up the top of the hour, so I would encourage folks with those to contact you directly. You've got your contact information up on that last slide. Also, for those who want to kind of go back and listen to specific parts of this or refer this presentation to your colleagues, it will be well, probably later today, but it will be available on FOSA's web page and also through, actually primarily through our YouTube page, which is passed off from our website. So that will be available in the future. Now, we do have a number of webinars scheduled for the next couple of months. We've been able to plan a little farther in advance. Coming up on February 20th, is a webinar on breakthrough research in DAS for third-party intrusion detection, and this is with Duraline, Photech, and OFS. We also have another one on March 19th, which is fiber optic sensing for power transmission. This is with NKT Photonics, and this, of course, obviously focuses on a different use case. And then on April 16th, Ditch Witch will be conducting a webinar, I assume on some retrofit issues, something that we sort of talked about at the very end with that question. So Chris, thank you very much, as always, for a very informative presentation. I think even those who know a fair amount about the field learned a lot from it. Thank you, and that concludes this webinar.